Sometimes, if you touch a metallic doorknob or any metallic object, you might experience a mild shock. This is because the metallic object was charged, or in other words, it carried an electric charge. Objects that carry an electric charge are said to be electrically charged. We know that when a comb is rubbed against dry hair, it begins to attract small pieces of paper. When two pieces of silk cloth are rubbed against two glass rods individually, and the glass rods are kept beside each other, the glass rods repel each other. Now, if one of the silk cloths and a glass rod are kept beside each other, they attract each other. Now, bring one charged glass rod in contact with a pith ball and then separate them. Then bring the other charged glass rod in contact with other pith ball and then separate them too. When these pith balls are kept close to each other without contact, we observe that they repel each other. The physical quantity responsible for all these phenomena is known as electric charge. Electric charge can be defined as the property of matter that exhibits its electrostatic interaction with other matter. From previous examples, bodies like combs, glass rods, silk cloth pieces, pith balls, etc. are said to be electrified or are called charged bodies. The study of electric charges at rest and the physical quantities associated with electric charges at rest is called electrostatics or static electricity. These experiments prove that a body can be charged by rubbing against another body or by simply bringing a charged body in contact with another uncharged or neutral body. When the glass rod and silk cloth were first rubbed, they get electrified. But when they are brought in contact again and separated, they lose their electrification or charge and are neutralized. In other words, the charge on them is nullified. Hence, we can conclude that one of them may be positively charged and the other negatively charged when they are rubbed against each other. From these observations, we see that there exists only two types of electric charges in the nature. Conventionally, they are called positive and negative. It is also observed that the like-charged bodies repel each other. For example, two pith balls, both carrying like charges, repel each other. Unlike charged bodies attract each other. For example, a pith ball carrying a positive charge will attract a negatively charged pith ball. We know that all matter is made up of atoms or molecules. Also, within an atom, the total negative charge is balanced by the total positive charge in it. When we rub one material against another material, the material in which electrons are relatively loosely bound to its atoms readily loses a few of its electrons to the other material. the material that lost electrons now has a deficit of electrons and hence becomes positively charged. And the one that gained electrons becomes negatively charged. In this case, the glass rod lost electrons and became positively charged, and silk gained those electrons and became negatively charged. To know whether a body has been charged, we use an instrument called a gold leaf electroscope. It consists of an insulated metal rod with 2 gold leaves or foils at one end and a metal disc at the other end. This setup is enclosed in a glass jar with the help of a tight cork with the disc placed out of the jar. To test a material like a glass rod for electrification, the object should be brought in contact with the metal disc of the gold leaf electroscope. The contact should be momentary. If there is no change observed in the position of the gold leaves, it indicates that the glass rod is uncharged or is neutral. If the gold leaves repel each other, then it indicates that the glass rod is charged. The amount of divergence provides a rough measure of the charge on the glass rod. Assuming that the glass rod was positively charged, the gold leaves now carry a positive charge. Now, if we touch the metal disc with the silk cloth used to rub the glass rod and take it away, we observe that the gold leaves fall back to their original position. Thus, we can say the silk cloth was negatively charged. On contact, the opposite charges on the gold leaves and the silk cloth nullified each other. We know that electric charges are conventionally called positive and negative charges, and that like charges repel each other and unlike charges attract each other. However, if the size of charged bodies is very small, but the distance between them is comparatively larger than their sizes, such charged bodies are treated as point charges. Coulomb, C, is the SI unit of electric charge. However, smaller units such as microcoulomb and millicoulomb are also used in electrostatics. Electric charge is a scalar quantity, which has only magnitude but no direction. Hence, the total charge on the body is equal to the algebraic sum of the individual charges given to it. Let us illustrate this with an example. Consider a body carrying a charge, say Q1. We add another charge Q2 to this body. Now, the total charge on the body is the algebraic sum of both charges. That is, total charge Q is equal to Q1 plus Q2. Similarly, if a body carries n number of charges, Q1, Q2, and so on up to Qn, then the total charge on the body Q is equal to Q1 plus Q2 plus Q3 and so on till Qn. While adding the charges, proper signs should be used. A positive sign for a positive charge and a negative sign for a negative charge. We can determine whether a body is charged positively or negatively by finding the algebraic sum of all charges on the body. For example, if a body is given 6 charges, all in coulomb, say +1, -2, +3, -4, -5, +6, the algebraic sum would be -1 coulomb, which means it is a negatively charged body. Another property of electric charges is that the total charge in an isolated system is always conserved. When a glass rod is rubbed with a silk cloth, electrons are transferred from the glass rod to the silk cloth. Now, both the glass rod and silk cloth are charged. Here, there is only a transfer of charge taking place. Neither is a new charge created, nor is any charge destroyed. The number of electrons lost by the glass rod is equal to the number of electrons gained by the silk cloth. If we consider the glass rod and silk cloth as an isolated system, then the total charge of this system before and after rubbing remains the same. Therefore, we can conclude that the total charge of an isolated system is always conserved. Similarly, charges are also conserved in natural processes such as the beta decay of a neutron. During the beta decay, a neutron breaks into a proton and an electron, releasing a neutrino. Here, the neutron and neutrino are chargeless particles, while the proton and electron are oppositely charged particles, whose combined net charge is 0. Hence, we observe that the total charge in this process is conserved. The charge on an object is measured as an integral multiple of the basic unit of charge that the proton or electron carries and is denoted by E. This property is called quantization of charge. The magnitude of the basic unit of charge E is approximately equal to 1.6 into 10 raised to power minus 19 coulomb. In an atom, when we refer to the charge on a proton, its value is positive and is referred to as plus E, whereas the value of E for a charge on an electron is negative and is referred to as minus E. Thus, the charge on an object Q is equal to the product of the number of electrons gained or lost by it, N, and the basic unit of charge, E. Now, let us calculate the number of electrons 1 coulomb of negative charge carries. Consider a body possessing a charge Q equal to minus 1 coulomb. Let the number of electrons it has gained to become negatively charged be N. As the charge Q on a body is quantized, we have Q equal to NE, where the basic unit of charge E has a magnitude of 1.6 into 10 power minus 19 coulomb, and Q equal to minus 1 coulomb. Substituting the values of Q and E and simplifying, we have N equal to minus 6.25 into 10 power 18. Here, N is a negative integer, indicating that the body has gained a negative charge. So, we see that 1 coulomb of negative charge contains 6.25 into 10 power 18 electrons, which is a very large number of electrons. In the practical examples we have seen for charging a body, we deal with bodies possessing a charge of about a few microcoulomb. the charge of microcoulomb, that is 10 to the power of -6 coulomb, is very large compared to the basic unit of charge E. When such a microscopic level of charge is involved, the concept of quantization of charge can be ignored, since it has no practical significance, where we say the charge is always added or removed in integral multiples of the basic unit of the charge. Quantization of charge is significant only in the microscopic sense. When the charge possessed is due to a few hundred times the basic unit of charge E, or even less than that. Let us now learn about conductors and insulators. We know that atoms are the basic building blocks of all matter. In an atom, the protons and neutrons are the constituents of the nucleus, while the electrons revolve in orbits around the nucleus. For some materials, generally metals, the electrons in the outermost orbit are loosely bound to the nucleus, and these electrons are called free electrons. These electrons are relatively free to move around the material. Such materials with a large number of free electrons are called conductors, and as such, these materials readily allow the flow of electric current through them and cause very little resistance to the flow of electricity. Metals like copper, nickel, and the human body and earth, etc., are some conductors. Some materials have a very small number of free electrons, and hence offer very high resistance to the flow of electricity.